Hello, my dear. Hello, my dear. Welcome to IMS GATE Academy. I hope you are all good and your preparation going to be in a right direction. I am Pragyabrat Tripathi, Faculty Department of Mechanical Engineering. So today we are going to with the same topic of a thermodynamics to the continuity, and in this case we also will discuss the entropy, and we have successfully do that this one. That means we have TDS relation. Okay, we have a TDS relation. In that relation we have to find different things. Okay, so there are two things in a certain, there are two things beta. What is that? Number first, we have to do this one. That means, see, we know that beta, okay, so we have already seen that either a open system or a closed system. Okay, that means if we take this one, this is very important thing I am telling you. Many students get confused here कि sir TDS equal to du plus PdB and TDS equal to dH minus VdP. These are two relations and these are the properties relation, and these properties relations are valid for any process, any kind of the process, and these two are relation also applicable for any type of system. Mind it, it is not necessary that TDS is equal to DH minus VDP will applicable only for open system and TDS is equal to DU plus PdV applicable for closed system. No, it is wrong concept. So keep in mind, that is the one note here. What is that? I will write one note here. Okay, this is your note point. What is that? See, if this is your one is the closed system, that means if this is our, we make a closed system, that means this is our piston cylinder and this is our piston. So precisely this is our closed system. Okay, and if you take, there is an open system, that means control volume system. That means if we take, this is our control volume system. Let's suppose this is our control volume system. Okay, so this is our control volume system. That means something is in here. Let's suppose this is our inlet and this is our exit. Let's suppose this is our expansion kind of, let's suppose this is a turbine like that. Okay, so this is our system. Okay, this is our system, and this is a which system? Control volume system. Why? Because there is a something fluid is in here and something fluid is out here. Okay, so this is in and this is out, and in this case there is a closed system. This is our closed system. This is our closed system. Okay, closed system. Okay, in both cases, in both of the cases, we can say that TDS is equal to du plus PdV and TDS is equal to dH minus VdP. Mind it, in both the cases, it is not necessarily that this equation is valid for the closed system and this equation is valid for no. And this is the property relation and it is applicable for any kind of the process. Number first. Now, this is what is, see beta, this is very powerful equation. You can solve maximum things in the thermodynamics with the help of these equations. How? We'll see some few examples. Okay, let's suppose incompressible substance. Okay, incompressible substance. Incompressible substance. We take incompressible, that means volume is constant. That means the system have a fixed volume, constant. If the density is constant, that means a specific volume is fixed. Okay, why? Because we know that specific volume of the system is equal to 1 by density. Okay, we know that. This is the very good relation. Okay, always remember like that. Okay, no problem at all. Now, if the volume is constant, beta, which substance? Like liquid and solid. Liquid and solid. So it is our hand which equation you can take for the easily application. So beta, if volume is constant, then d of v is equal to 0, yes or not? So if you have this information, so it's your choice which equation we will use, so that our calculation, our effort is less. So which equation you can use? This first equation. Why? Because in this case, this third term, that means TDS is the first term, is equal to du is the second term, and PdV is the third term, will disappear. This third term, PdV is disappear. Why? Because dV is 0. So it is our hand which equation we can use. But in this equation, all these three have present there. Okay, why? Because this is a dP, not dV. So we can, which equation we can usually apply for this situation? We can use the apply equation TDS equal to du plus PdV. So my dear, it is very important in which situation you are working, and accordingly that situation you can apply this equation. Accordingly that situation. So in this one we can apply, and also we know that for the incompressible substance, Cp specific heat at a constant volume and Cv is equal to C, that is, this is constant specific heat. This is for the incompressible fluid. You also noted that here. Now, what is the du? We know that. What is the du? C into delta T, yes, C dt, d into T. Why? Because this is not Cv, yes, Cp, this is constant. So we can write. So this is first observation, this is the second observation, and this is third observation. Okay. Now we can apply, this is first TDS equation and this is second TDS equation. So we can apply first TDS equation. What is that? TDS is equal to du plus PdV. Okay, for any kind of the process. For any kind of the process Okay, for any kind of the process. Now this term is 0. Why? Because incompressible. Yes or not? Incompressible substance. Okay. So what is your relation? TDS, and what is du? C dt. Okay. Now you can easily solve this equation. So what we can write here? ds is equal to C dt by T. Okay. And C is the constant. Now, if we integrate from the process 1 to 2, that means the system will undergo the process 1 to 2, we can write here like that, कि sir, delta S is equal to integration 1 to 2 ds is equal to, C is the constant, you can 1 to 2 dt by T. You can write like that. You can write like that. Now, what is the change in entropy from point 1 to point 2? C ln T2 by T1. That means for the incompressible substance, the change in entropy, that means S2 minus S1 for the any process is equal to specific heat of the substance ln final temperature by initial temperature. Okay. Okay, this is for incompressible substance. And what is the C? C is the specific heat of the substance. This is your specific heat of the substance. So we can use like that, no problem. We can use this equation, no problem. Okay. So this is the application of this equation. So if in any system, if we want and that system have a fixed volume, that means system, it is for the volume constant, that means the volume is not changing of the fluid. In that situation, what is the change in entropy? C ln T2 by T1. T2 is the final temperature, T1 is the initial temperature. So if final temperature at anyhow will increase, the system entropy will increase. If the final temperature is decreased, the system entropy will decrease. And if there is no change in temperature of the incompressible fluid, that in that case the entropy is constant. That means if, see my dear, if we take the process, this is very important. Now we take the isentropic process. If we are doing the activity, that means for incompressible substance, for the incompressible substance, if you're doing an activity like that, its entropy never change. Let's suppose its entropy doesn't change. So if the entropy doesn't change, so T1 equal to T2. That means it in temperature will also doesn't change. That means in this case, temperature also doesn't change. That means if we take like that, note, very important, I'm telling you. What is that? For isentropic, if process is isentropic, right? That means if process, what is the process? 1 to 2. That means if process 1 to 2 is isentropic, that means delta S is equal to 0. If the process 1 to 2 is isentropic, that means delta S 1 to 2 is 0. Okay. Now that means what is the entropy change of incompressible substance? C ln T2 by T1. Now process 1 to 2 is isentropic, that means it is 0. Why it is 0? Why? Because isentropic process. Isentropic process, okay? Isentropic process. So in this case, what is that? So if you put this one, that means T2 is equal to T1. That means if system see my dear, it is not isothermal. See the beauty, is it not isothermal? That means temperature of a substance initially, final is the same as initial if there is no change of entropy. That means if there is an incompressible substance, and that incompressible substance have the process is isentropic, in that case its temperature final doesn't change. That means it is not like isothermal. In the isothermal, T1 to T2, each and every locus have its same temperature. That means hence incompressible substance temperature remains constant during isentropic substance. That means what is your observation? This is very important observation, beta. That means for incompressible substance, that means you can write here. What you can write? You can write here, beta. For incompressible substance, that means for incompressible substance, for incompressible substance, the temperature remains constant. Temperature doesn't change during during isentropic process. During isentropic process. This is very important, but only for, it is applicable for incompressible substance. This is important, beta. This is very important. Okay. So, this is the implication of the TDS equation. Now beta, one thing also noted here, if the process is isentropic, then gas is ideal. That means we can write also, there is a one relation. What is that? This is very important relation. Entropy change, we cannot here derived, only we can write here, no problem. Okay. So, what is that? The first equation, this first, that means we can write like that, beta, T2 by T1, final temperature T2 by T1, that, and this is for the adiabatic, T2 by T1 is equal to P2 by P1 is equal to V2 by V1, and all are in the isotropic. That means V2 by V1 you can write. Yeah, you can write V1 by V2, no problem. V1 by V2. Why? Because P and V are the product relations, so it is inversely. And these all are entropy constant, entropy constant, entropy constant. These all are entropy constant. And if you write the relation, this is your gamma minus 1 upon gamma, gamma minus 1 upon gamma. You can write K also, not gamma, you can write K also. Why? Because K is the polytropic index, K is the adiabatic index. So, gamma is also adiabatic index, so gamma, and here you can write gamma minus 1. Always remember gamma minus 1. This is always remember. That means T2 by T1, P2 by P1, V1 by V2, gamma minus 1 upon gamma, and gamma minus 1. You can solve many problems of the previous year GATE question, okay. So, what is this validity? What is this validity, beta? See, my dear. So, what is the validification of this equation? See, under which condition this equation is applied? Under which condition? Okay, in gas which is incompressible, how can we see that? No. We cannot take as a gas. See, in a gas which is incompressible, a gas which is, one second, in gas which is incompressible, how can it be isentropic as temperature change? How can it is, yes, I will, only for the ideal gas. Yes, only for the ideal gas. We'll take like that. That means for compressible, if gas is a compressible, okay, gas is compressed, either ideal or non-ideal, gas is a compressed. Or if, can it be isentropic as a temperature change? Once this is, when it is happening, we'll check. Only if we take a isentropic equation, then, this is applicable only for ideal gas, mind it. I will give you one example for that one. Just do this one. Valid for, one second, I will give you a reply, beta. Valid for, under which situation this is valid? I will just give you a reply, no problem. That means ideal gas, second one is the isentropic process, and third is your constant specific heat. Constant specific heat. Why? Because that specific heat doesn't depend upon the temperature. constant. This is very important line. Now I will come. I take your question. See, my dear, for the ideal gas, we know that entropy change. That means there are Cp, Cv, R, Ln. That means if you write that for ideal gas, this is very important, beta. For ideal gas. Now, for the ideal gas, Cp, Cv is that depends upon the temperature. But the ideal gas, we can say that if in general, if it is doesn't change with the temperature much more, doesn't depend upon the temperature much more, that means in that condition, if you write a entropy change of the process, that means S2 minus S1, this is also important. This is also important, I am telling you. This is also important, beta. S2 minus S1, that means S2 minus S1, it have a different form. Cv, that means Cv, Cp, it is not incompressible. It is a compressible. For incompressible, Cp, Cv is same. Okay. So this is a compressible. These all are the compressible fluid. Cv, Ln, V2 by V1 plus R Ln, R Ln, not V2 by T, this is a T2 by T1. 1 second. This is what? Okay. T2 by T1, T2 by T1, R Ln, V2 by V1. This is the first relation. Second relation, S2 minus S1, we can write in the form of Cp. So if we write Cp, Ln, T2 by T1, here you write minus R Ln, P2 by P1. Now I will come your question. Now beta, see my dear, how to remember this equation? If you write Cv, so V2 by V1. If you write Cp, so P2 by P1. Okay, and why it is minus? So if you Cp, then there is a minus. So what is the now? Under which condition it is valid? Under which condition it is valid, beta? Under which condition this is valid? Now, in gas which is compressible, this gas is compressible. How can it be isentropic as temperature change? As temperature change. That means if the temperature change, it is not isentropic. No. How can it is isentropic as a temperature change? No. For the compressible, this is a compressible. If the temperature is changing, and change in pressure and volume are fixed. That means if you write in the third relation like that, so this is for ideal gas. It is not like that. Ideal gas. This is for ideal gas. And it is not a constant specific heat, my dear. We cannot say that if there is a compressible fluid, if we compress it, can we write Cp ln T2 by Cp ln T2 by T1 plus R? No. If you reverse R, okay, no problem. We can write here. If you reverse it, we can write it. If you reverse it, we can write. Okay, no problem. T2 by T1, P1 by P2. We can write it here, no problem. If you reverse it, we can write. We can write, Pratik. This is your log rule. If you reverse, now if we reverse, all the things are reversed. We can not write here. If you reverse it only it, if it will reverse, it also will reverse. It is the beauty. If it will reverse, it is also reverse. Why? Because see, for ideal gas, what is that? PV is equal to mRT. So P and V are both are equal. That means if you write P1, write T1. If you write P2, write B2, T2. But in the case of if T2 same V2, so T1 same V1. So these are the directly. This is the right question. Atul, this is the right question. Now, from here, we can say that this entropy change for the system. Now, if the system, what is the system? See, my dear, if this is a system, that means if we take this is our system and this is our surrounding, we can write like that. But if we take an isolated system, we can write also. It is not that we can apply for any type of system. This equation, see my dear, from where it is come? From here. From this one it is come. So this equation is applied for the system and any type of system, either closed system or open system or isolated system. We can write like that, no problem. So Atul, your answer is this equation is applicable of a system or a system which is included a surrounding also. That means this is for the system plus surrounding. And system plus surrounding, it is also act as a system. So in this case, this change in entropy is always greater than equal to, that means this is always greater than equal to 0. But in this case, if you apply for this one, in this case, this change in entropy is greater than 0, less than 0 or equal to 0. All the cases are possible. Doesn't matter which system you can apply. In this system, it is greater than equal to 0. That means this value change in entropy is greater than equal to 0. Not less than. Why? Because it is a globally and this is your locally. So locally system entropy can be increased, decreased or equal to 0. But globally system entropy always increase. That is called increasing principle of increasing entropy. Right? So you can use for both of this one. This is a very good question where a student get confused. Okay? Now Atul, okay, it is okay, beta? It is okay? It is okay now? Now, if you find, that means this is a very important equation, beta. We know that PV is equal to PV per power gamma. That is for the, if you write the equation for the ideal gas, this is very important. I am telling you, very subtle concept there. If you write PV per power gamma is equal to constant. If you write this equation, this is very simple equation, but there have an insight. Okay. Now tell me, under which condition this equation is applicable? Tell me, just tell me. Under which condition this equation is valid? Under which condition this equation is valid? This equation is valid for first ideal gas, second, this is simple, second, reversible process, third one is adiabatic, boundary, that means in which there is no heat transfer. Right, we can write. And what is gamma? In this equation, what is gamma beta? It is constant or what? Okay, Pratik. For the polytropic process. This is for polytropic. This is for polytropic. Yes. Adiabatic boundary. It is not adiabatic process. Adiabatic boundary. Polytropic process is it not applicable? Why? Because while we driving this equation, very important. While we driving this equation, in this equation we can take heat transfer is 0. That means if you apply TdS is equal to du plus PdV. Okay, and in this condition, this is 0 for reversible adiabatic. Reversible plus adiabatic. Not polytropic. Not polytropic. And this is what? This is what? CV. That means mCV dt. Why? Ideal gas. Ideal gas. This is for ideal gas. In that condition, we can apply this equation. This is a reversible adiabatic, not polytropic, my dear. This equation is not applicable for the polytropic. Mind it, Pratik. Accordingly, we can derive it. Gamma is the adiabatic index, and in this equation, this is very important observation. I am telling you, this equation gamma, no matter it is constant. Gamma, no matter it is constant. Okay, so this is not applicable for the polytropic process. No, it is applicable for the adiabatic process, and that adiabatic is reversible. Now, if you have this equation, if you have this reversible adiabatic process, and if you find the work, work transfer. If you find the work transfer, what is the value? We know that work transfer process 1 to 2 is equal to P2 V2 minus P1 V1 divided by gamma 1 minus gamma. Now, my dear, tell me, this is very important observation. This equation. Now, we can derive this equation for the reversible adiabatic, but this is applicable for any process, either reversible or irreversible. This is very important, I am telling you. And in this case, gamma is constant. So, there have a very good, and also we can write here MR, not MR T2 minus T1 1 minus gamma. We can write it. Now, this equation, this is very important. This equation is applicable in which condition? My dear, this is very work is equal to P2 V2 minus P1 V1 1 minus gamma. No. 1 minus gamma. P2 V2 1 minus gamma beta, not gamma minus 1. Not gamma, 1 minus gamma. This is very important. How can you write? This is proved. 1 minus gamma, it is right. If you write gamma minus 1, there is a T1 minus T2. If you write gamma minus 1, there is T1. 1 minus gamma, always right. 1 minus gamma. Please verify. Atul, it is true or what? It is true or what? This is right. No confusion. What I am writing here, that is absolutely right. 1 minus gamma. That is absolutely right. Okay. Now, give me a reply under which condition this is applicable. This is for adiabatic. Number first. Number second, ideal gas. Ideal gas. Number third, very important, very important, gamma constant. And beta, that is the last assumptions which is have many students get confused here. What is that? What is that? See, that means no matter it is a reversible or irreversible process. No matter it is reversible or irreversible process. I am telling you, this is very big confusion of the student community. See, this is derived by the reversible, this is the reversible, but once it is derived, this is applicable for any process that we can prove by the reversible. That means this work is applicable for the reversible adiabatic process, and also this work reversible is applicable for the any adiabatic process. This work transfer is applicable for the reversible adiabatic process, and this work is also applicable for the any adiabatic process. This is very clear about that, where a student get confused. Sir, this is only applicable for the reversible. No. This is applicable for any adiabatic process. That means any adiabatic process. In the regular classes, what I am taking the regular class, not YouTube class, we prove that we can prove here. At that point, at that time, we have to prove why it is. If you take one case reversible adiabatic, and if you take other case any adiabatic process, in both the cases this formula is same. So this is the second subtle concept is there. Now my dear, if you know this thing very correctly, so this is all about your work transfer. This is very important in many thermodynamics process. In many situations of the thermodynamics process, these concepts are useful to you, and that is the very subtle concept is there. Very subtle concept is there, I am telling you. These all are the very subtle concept is there, okay? Now my dear, now we take a second observation. What is that? We take it is visible, na? Yes. We take change in entropy for an irreversible process. This is very important. Okay, for an irreversible process. Now, generally this have a little bit analysis in between that few moment in between few lines, so we can also apply for that one. See, this is for process. So in any thermodynamics, if you prove for any property if you find any property, change in property for an irreversible process, there is a common method. What is the common method? You are draw a cycle, and that cycle is connected through a process by a reversible, and that cycle also connected through a process by an irreversible. Then you can find for any process. In anywhere of thermodynamics, if you find the property change for irreversible process, it's your technique that you can draw a cycle of the same state point with one reversible and other is irreversible, and accordingly you can prove. That is the subtle concept. That means if you write, this is your, let's suppose y and x. Let's suppose this is your y and x, any property y and x. And let's suppose x is the entropy change. Now, if you take a state point 1 and this is a state point 2. Now, in the state point 1 to state point 2, we can design a cycle for the reversible manner. This is for the reversible A and B. This is a reversible cycle, and we can draw also in a irreversible manner. In a irreversible manner. So this is another process which is in irreversible. Which is irreversible. So this is your irreversible dotted line. So this is your irreversible. So in this condition, there are two cycles. This is your C. 1 to 2 via A plus B is the reversible cycle. 1 to 2 via A plus C is the irreversible cycle. Okay, and three process, three path A, path B, and path C. So we know that from the second law of thermodynamics, for reversible cycle, what is for the reversible cycle? And what is the reversible cycle? A plus B. Okay. And for the reversible cycle, what is we know that? Cyclic integration dq by t for the reversible is equal to 0. We know that this thing. This is the clauses. So if we split this cycle into the process for the reversible manner, that means 1 to 2 via path A dq by t plus reversible 2 to 1 via path B dq by t, and this is 0. Okay. Now for irreversible cycle, that means A plus C. For the irreversible cycle, that means A plus C. So this is an irreversible cycle. So for the irreversible cycle, we know that what is that dq by t, please? What is the dq by t, please? For the irreversible cycle, what is dq by t, please? Reply in the chat box. What is dq by t? What is dq by t? Less than 0. Less than 0. Now split into the process. That means process 1 to 2 via path A dq by t plus process 2 to 1 via path C dq by t, and this is less than 0. Okay. Now you can compare this first equation and second. With the help of this first two equations, that means from here we can write process 1 to 2 A dq by t is equal to minus 2 to 1 of B dq by t, and put here, and then you solve it. So if you rearrange that, that means after rearranging, after comparing first and second, what we get? We get process 2 to 1 via path B, via path V, dq by t is less than 2 to 1, sorry, this is C. 2 to 1 via path C is less than 2 to 1 via path B. See, my dear, B is the reversible process. See, B is the reversible process and C is the irreversible process. That means there is one conclusion is that. Someone asks you like that, ki beta, if this is your thermodynamic TS and if there is a 1 to 2, this is your 1 to 2 and 1 to 2 joined by a reversible manner and 2 to 1 joined by a, this is your reversible A to, this is your B, let's suppose. What's your conclusion? And both are the same direction. Let's suppose, see my dear, this is also important. Both have a same direction. That means you cannot draw like that, okay? That means both are the same direction. That means you can write like that. Let's suppose this is your 1 and this is your 2. Let's suppose 2 to 1 via a, let's suppose 2 to 1, let's suppose 2 to 1, yeah, 1 to 2 same situation. You can write like that, no problem at all. 1 to 2 same process A reversible and 1 to 2 process B irreversible. So what is the that inequality? So we can write here 1 to 2 via path A dq by t always greater 1 to 2 via path B dq by t. This is very important, I am telling you. This is very important, okay? Many students get confused here. This is always true, okay? So for the reversible, this is a reversible path 1 to 2 dq by t is higher than the for the irreversible path 1 to 2 dq by t. This is very important analysis for this one. So B is a reversible, that means this is a reversible, B is your reversible, so this is your reversible path and this is your irreversible path. This is very important observation. This is the first observation you can observe like that, okay? So for the irreversible path, path dq by t is higher than for the irreversible path. Now my dear, so this is your B. So this is your reversible. If this is your reversible, what we can write? So we know that for the reversible, delta S is equal to, yeah, we know that for the reversible, ds is equal to dq by t. And mind it, it must be internal reversible, okay? So this we can write here. So dq by t we can write ds. Yes or not? We can write ds. Very important analysis. So in this situation, we can write like that. for this one, that is this one, this whole quantity. We can write like that. Two to one for the reversible, that means this is your B. dq by t we can write ds. Yes or not? We can write like that ds. Now very important. This is what beta? ds 2 to 1. That means ds 2 to 1 via path B. That means, see my dear, ds 2 to 1 via path B. So this is your S1, this is your S2. So this is your ds. Yes or not? So ds for path B and ds for path C are same. That means we can write cyclic integration 2 to 1 via path B of ds is equal to cyclic integration 2 to 1 via path C ds. This is very important, I am telling you. But if you write dq, so dq for the path this one is greater than the dq of path this one. This is very important relation. So why? Because this ds is the entropy. So ds is equal to change in the property. What is that? Change in property. Change in property, and change in property is applicable for any process. So this is for reversible and this is irreversible. So this is the second equation, and if you write in the form of it, this is in this equation, this final. Okay, so we can write here, sir, this is 2 to 1, also we can write C ds. Why? Because entropy is the property. Now, if you compare this one, if you compare these two, what you can write here? You can write here like, that means this is your 2 to 1 C dq by t is less than 2 to 1 C ds. Yes or not? Yes or not? So this is your second relation. So this is your second. So this is your first observation. This is your first observation. This is your path in for path A is higher than path B. This is your second observation. This is your second observation. That means if you write 2 to 1 via path B is equal to 2 to 1 via path C. This is your second, and this is your third. These are the third. This is very important, I am telling you. This is very important. So from here we can write here, so 2 to 1 ds is greater than 2 to 1 dq by t. Okay, dq by t, and this ds is the for any process. This ds is for any process, any path. But this, so if you integrate it, if we integrate it, how to write here? Now, if we integrate it, so this is your delta S is greater than, this is your what? Del q by t. Okay, we can write like that. We can write like that after integration. Now, if we write equal, if we write delta S, this delta S is for any process. So, for any process, if you write dq by t, so from here, if you write in equality term, delta S, if you write equality del q by t, you must add something here. You add something, a positive quantity. Positive quantity. Or we can write here. Here we can note. So, for if you write equal, so from here we can add a positive quantity. Right? We can add here a positive quantity for the equality. Now, what is that positive quantity? What is that positive quantity? Which you have to lost. Which we have to lost. We can never, this quantity is can never we can take as a, this is a lost opportunity to do work. That means this is a lost work. That means if you write delta S is equal to del q by t, and that is the positive quantity, that positive quantity is right here is generation. This is your generation, entropy generation. Okay. Cycling. Cyclic integration. Yeah, you are always saying cyclic integration. The closed path, correct? How to differ from the normal integration? It is because we can apply Simpson's 1/3 rule. In this region, we can use cyclic integration. Yes, let us see what is that. What is that? If this were cycle, see, this is your y and this is your x. So, 1 to 2 and 2 to 1. Okay? 2 to 1. So, A and B. So, this is a closed loop. 1 and 2 to 1. That means you can reach 2 to 1. And this is your contour over a path. So, if we see beta, if we write path, to integrate 1 to 2 something quantity, let's suppose dx for the path A, right, plus 2 to 1, this is a cycle rule, for the path B dx. It is right. It is right. If you integrate path 1 to 2 dx, if you integrate path 2 to 1 dx. Now, if you combine this one, so this combination, how can you write? This is cycle. What I think you, what is this one? What is this one? This is the summation over the cycle. So, this is your summation. This notation is the summation. Summation over the cycle. So, this is your summation over the cycle, and this is how can you write? So, cycle cycle integration. Now we cannot write 1 to 2 is dx. What is the problem? What is the problem? So you always saying the cyclic integration. Yes, it is a cyclic integration. And path is all, if you make a cycle, that cycle have a different path, and that path is finally closed. And normal, this is a cycle. That means this is a contour over the contour. That means if it is look like that, let's suppose 1, 2, 3 and 4. This is cycle. So we can use this one by A, B, C, D. Okay, so net change is what? 0. Positive, this is negative, cancel out. This is positive, this is negative, cancel out. So net change in x is 0. That means finally it is at this point. So if we write process A, process B, process C, process D, that means this is 1 to 2, 2 to 3, 3 to 4. So if we write process 1 to 2 via path A, plus process 2 to 1 via path B, plus process 3 to 4 via path C, plus process 4 to 1 via path D. And that are all the integration, summation. And now if you take total cycle, that means in this case we can write cycle of dx. If this is your x, what is the problem? What is the problem? No problem anymore. And that cycle is equal to same is the cycle integration of dy. Same is thing. Why? Because if you write t and if you write s, so if you write t and s, so what is that? If you write cyclic integration of ds is equal to 0. And if, so cyclic, so if you write a cyclic, this is 0. For the reversible path, cyclic integration ds is equal to 0. Why? Because it is a property. No problem at all. No problem at all. Okay. So this is your entropy. Mind it. This is the, what is the generation? This is your generation. So first, see, this is your change in entropy of which one? Of the system. Change in entropy of the system. Now, my dear, I give you a very subtle concept. What is T? What is T? First tell me. What is T? Now, what is this GS? Now, this is a generation. This is a very important concept. I am telling you, very important concept. Just hold on. This is a very important concept which we will discuss here, and you can never found in the any other source. See, my dear, this is very subtle concept. I am telling you, never seen in the YouTube channel anywhere. What I am telling you. See, let's suppose there is a piston cylinder arrangement. Let's suppose there is a piston cylinder arrangement, and this is your system. Now, okay, this is your system, and this is your system, let's suppose, and there is a surrounding. Let's suppose this is your surrounding. Entropy generation due to mixing also. Entropy will generate due to mixing. Entropy will discuss just now. Just give me a short. I will discuss this one in a very heavy dose. No problem. You feel it. No problem. But just now, what this equation is says, I am just telling you from the practical example. Okay, hold on for a 2 minute. Now, this is your system. Now, if this is your reservoir, so let's suppose this reservoir, this is your reservoir. This is your reservoir. Let's suppose this reservoir have a temperature 100,000 Kelvin. Let's suppose this is your 1000 Kelvin. Let's suppose. Now, this system have a temperature, and that temperature will, this system have a temperature, the system have a temperature, and what is the temperature? Temperature, it is less than 500 Kelvin. That means T of system is equal to 500. Let's suppose. So in this manner, heat will transfer. In this manner, heat will transfer. Heat will transfer. Let's suppose heat will transfer is equal to 1500 kilojoule. Okay. Let's suppose heat will transfer 15. Now, my dear, tell me one thing. Just be ready for this subtle concept. Okay. Okay, my dear. Now, if we write the equation delta S is equal to delta Q by T plus S generation, entropy generation. First, tell me, if you write this equation, okay. Now, this is the entropy change of the system. Okay, this is the entropy change of the system, and this is the generation, entropy generation. So, what is this temperature? Just tell me, what is this temperature, beta? Which temperature we can put here? Which temperature we can put here? Just tell me. There are 3 temperature: system temperature, surrounding temperature. Sorry, 2 temperature. So, system temperature, that means system boundary temperature, it is given. Reservoir temperature, it is given. Which temperature you can put? If you find the system entropy change, which temperature you can put here, beta? Please. Please tell me. Which temperature you can put? Please reply, Pratik. Which temperature you want to put here to calculate delta S? Yeah, to calculate S generation. What do you know that? Frequently, which temperature you can put? That means, you can say that, okay. That means, okay, hold on. That means you say that, sir, this temperature T, we can put system temperature. Okay. 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 So, in this condition, what is the meaning of this generation here? What the meaning of this generation here in this case? If you put the temperature of system, what is this generation? What is this generation? Please tell me. This is the generation internal, very important. This is your internal generation. Now, but if you find the total generation, that means total. If you take this is our system, so you have a system temperature. Internal irreversibility. Right. Okay. Now, if you find total generation, total, what is the temperature here? if you find this total generation, if you find this total generation, what is the temperature here? What is it? Just tell me. Oh, very few time is there. What is the total generation? What is here? Temperature? Just tell me. What is this temperature? Is same or other? Please tell me. What is this temperature? Just tell me. Just tell me what is the temperature? Same or other than that? What is this temperature? We have to find that. If you find the total, that is the total. Please tell me. This is the temperature of surrounding. Very important, I am telling you. That means this is the temperature of surrounding. This is very important, I am telling you. What is the total entropy? What is the total generation? What is the total generation? That total generation is equal to S generation due to internal plus S generation due to external. Now, if we find, so beta, my dear, in this case, if we find the external generation, no. That T2 minus T1 we cannot put. This is the single temperature. In this equation, this is not a change in temperature. This is single temperature. We cannot put T2 minus T1. We cannot put T2 minus T1. Okay? We can never put here T2 minus T1. Never. Either this is a system or either this is total. So if you find a total generation, you always put temperature of the surrounding. If you find internal generation, you always put the temperature of system. No role of T2 minus T1. Number first. Number second. See, my dear, if you find external generation, first find internal generation. Number first, due to this condition. Now, so internal generation you have. Now, then you find the total generation from this equation, surrounding. Now, total generation multiply, subtract, in the total generation, subtract internal generation, then you find the external generation, my dear. This is the beauty of this question. First, find internal generation by putting the system temperature. Now you find the total generation by putting the surrounding temperature. Now the total generation minus, subtract the internal generation, then you find the external generation. This is a beauty. There are two steps of calculation. This is a very subtle concept I am telling you. You can never found on anywhere. Okay? Clear? Clear, beta? This is clear? Okay. So, now up to that, I end up here and will meet very soon for the upcoming lecture. Okay? Thank you. Bye-bye.